Again, good morning. For our last topic in our extension class, Statistics and Probability, we are going to discuss today what we call correlation. So by definition, a correlation is a relationship between two variables. Let us take the two variables age and weight. So if we'd like to determine whether there is a relationship between the age of a person and his weight. Now you're finding the relationship between two quantitative variables without being able to infer causal relationship. So we're not looking at the cause, we're simply looking at the variables itself. And as we say, it is a statistical technique used to determine the degree to which two variables are related. So if we're going to represent our data as an ordered pair in the Cartesian plane as x and y, then we will take x as the independent variable and y as the dependent variable. In the example I just mentioned, if we'd like to determine whether there is a relationship between the age of a person and his weight, then the age will now be our independent variable and the weight will now be our dependent variable. So for this study, we will only be using a bivariate data, wherein a bivariate data has or involves only two variables. So in the earlier example I gave you, age and weight, no other variables except age and weight. So a correlation of coefficient is a numerical measure to determine whether these two variables are related and the extent of the strength of the relationship. Would like to know if there is a strong relationship between the two. Now, a visual tool that can help in the analysis of the relationship between the two variables in a bivariate data is called a scatter plot. So a scatter plot is simply a diagram of points which we can now show in a Cartesian plane. So scatter plots are the most important graphical summary of the bivariate data, where we can see the association of trend between the independent variables and the dependent variables. So in a scatter plot, the pattern of data is indicative of the type of relationship between your two variables. They may either have a positive relationship, a negative relationship, or no relationship at all. So this is an example of a positive relationship. This is an example of a scatter plot with a positive relationship. You're going to notice that as the variable in the horizontal line goes up, the value of your grade in course or the one in the vertical line also goes up. So this is an example of a positive relationship. While if we have a negative relationship, you're going to see in our scatter plot that as the age of the car increases, then its reliability decreases. Now, this is an example wherein the points has no pattern at all. So there is no relationship between the weight and the pulse rate of a person. Okay, so for our example, let us construct a scatter plot that corresponds to the following data. So the weight in kilograms and the systolic blood pressure. If we're going to plot all of them, we're going to notice that if the weight is 67, then the systolic blood pressure is 120. So in our scatter plot, the weight is the horizontal line and the systolic blood pressure is the one on the vertical line. So if our weight is 67, then the systolic blood pressure is 120, the first point. Second, if it's 69, it's 125. So if it were 69, it's 125. 69 here and 125 there. So these are now the plotted points. This is how we do a scatter plot. a scatter diagram. So correlation is a linear association between two random variables. So correlation analysis show us how to determine the nature and the strength of the relationship between the two variables. When we use a measure of correlation to determine the strength of the linear relationship between two variables, and the correlation coefficient is a statistic showing the degree of relationship between two variables. Now, the known correlation coefficient is the Pearson product moment correlation coefficient. So, we will use the Pearson product moment. It measures the nature and the strength between the two variables of quantitative type. The nature, we'd like to determine if there is a positive relationship, a negative relationship, or no relationship at all. When we talk about the strength of the relationship, we're now determining whether the relationship is strong or weak, or how strong it is, or how weak is the relationship. So the correlation coefficient computed from the sample data measures the strength and direction of a linear relationship between these two variables. And the sign of R denotes the nature of association. So while the value of R denotes the strength of association. Now, we're going to look at it. The correlation coefficient ranges from -1 to +1. The value of the correlation coefficient can only be between 1 and -1. So again, the negative or the sign will determine the nature of the relationship, and the value will determine the strength of the relationship. So the value close to +1 signifies a strong positive linear relationship, and the value close to -1 signifies a strong negative linear relationship. When the variables yield the coefficient value close to 0, then there is no linear relationship between the variables. So if the value of the coefficient is close to 0, then there is no linear relationship between the two variables. So even if the two variables are linearly related, it does not necessarily mean that one of them is causing the change to the other. Other factors has to be considered. Now, again, if the sign is positive, the relationship is direct, which means that an increase in one variable is also an increase in the other variable. Or a decrease in one variable is also a decrease in the other variable. While if the sign is negative, it means that it has an inverse relationship, or which means that if one variable increases, the other variable decreases. Now you have to look at it in the same manner that you look at it in a variation. So if one variable goes up and the other goes up, we have a direct relationship. If one variable goes up and the other goes down, then we have an inverse relationship. So this is now our line wherein we show the values of our correlation coefficient. So this is our 0. From 0 to +1, we have a direct. From 0 to -1, we have an indirect relationship. So if we have +1, we have a perfect correlation. And if we have a -1, we also have a perfect indirect correlation. So looking at it, if it were positive, we know that it is a direct relationship. If it were negative, we know that it is an indirect relationship, which means that if one goes up, the other goes down. And then the value will tell us the strength of the relationship. So if it is near to 0, it's a weak positive. So from 0 to positive 0.25 is a weak positive relationship, while from 0 to positive 0.75 is a strong direct relationship. However, looking at the other side of the line number, from 0 to negative 0.25, we have a weak indirect relationship. If we have a negative 0.75, then we have a strong, more than that would be a strong indirect relationship. So if the coefficient is 0, this means no association or correlation between the two variables. If the value is less than 0.25 but greater than 0, then we have a weak correlation. If the coefficient is less than 0.25 but greater than or equal to 0.25, then we have an intermediate relation. If positive 0.25, if the coefficient is less than positive 1 but greater than 0.75, then we have a strong correlation. If we have the coefficient as equal to 1, then we have a perfect correlation. So how are we going to compute for the simple correlation? I have just prepared the formula for you. So remember that x and y are representative of our variables. So in the formula, the coefficient of correlation will now be equal to the sum of the product of x and y minus the sum of x multiplied by the sum of y all over the total number of data that we have. Everything divided by the square root of the sum of the square of x minus the square of the sum of x all over the total number of data that we have, multiplied by the sum of the square of y minus the square of the sum of y all over again with the total number of data. So let us look at our first example. A sample of 6 children was selected. Data about their age in years and weight in kilograms was recorded as shown in the following table. It is required to find the correlation between the age and the weight. Okay, we have 6 data. The age of 1 is 7, the weight is 12. The age of 1 is 6, the weight is 8. The age of the third data is 8, and the weight is 12. The age of the fourth child is 5, and the weight is 10. The age of the fifth child is 6, and the weight is 11. The age of the sixth child is 9, and the weight is 13. So the weight is now in kilogram. So what we need to do is fill out our table. So these two variables, the quantitative type, are variables. Age is the independent, denoted by x, and the other variable, weight, which is our dependent variable, is denoted by y. So variables to find the relationship between the age and the weight, we compute the simple correlation coefficient using the following data. Now let us now look at our table. So these are the number of child. We have 6 data. These are the ages of the children, and these are the corresponding weights in kilograms of our respondents. So we have in our fourth column, we need to multiply the value of our variable x and y. So 7 times 12 is 84. 6 times 8 is 48. 8 times 12 is 96. 5 times 10 is 50. 6 times 11 is 66. And 9 times 13 is 110. Getting the sum of the product of x and y, we get 461. So again, we notice that we got the sum of all the weights. We have 66 and the sum of all the ages is 41. So in our fifth column, we are now getting the square of x. The square of 7 is 49. Square of 6 is 36. 8 is 64. Square of 5 is 25. Square of 6 is 36. And the square of 9 is 81. Then I will also get the sum of this, which will give me 291. On our last column, we are now getting the square of y. So 12 square is 144. 8 square is 64. 12 square is 144. 10 square is 100. 11 square is 121. And 13 square is 139. Adding all of them, we get 742. And then we simply now plug it into the formula. So we have 461 is the sum of 461 is the sum of x and y. Here 461 is the sum of x and y. This is that minus 41 times 61 times the product of these two. 41 times 61. Everything divided by the square root of 291. 291 is the sum of the square of x. And 742 is the sum of the square of y. Okay. This is 41 squared all over 6 data we have. This is 66 over 6 data we have. Solving for it, we are now going to find that our coefficient of correlation is equivalent to 0.759. Notice again that the sign is positive, which means that there is a direct relationship. And because it's 0.759, then we have a strong positive or a strong direct relationship or a strong direct correlation. Okay, let us look at the second example. So, the relationship between anxiety and the test scores. This is now our table. Again, we have 6 data. The anxiety level is 10 and the test score is 2. If the anxiety level is 8, the test score is 3. If the anxiety level is 2, test score is 9. If the anxiety level is 1, the test score is 7. If the anxiety level is 5, then the test score is 6. If the anxiety level is 6, and the test score is 5. Again, we're going to get the sum of it. So 10 plus 8, 18, 20, 21, 26, 32. That's why it's 32. The sum of the test score is 2 plus 3, 5. 5 plus 9 is 14. 14 plus 7 is 21. 21 plus 6 is 27. 27 plus 5 is 32. Now, we now square x. So 10 squared is 100. 8 squared is 64. 2 squared is 4. 1 squared is 1. 5 squared is 25. 6 squared is 36. Adding all of this, we get 230. We now square y. So 2 squared is 4. 3 squared is 9. 9 squared is 81. 7 squared is 49. 6 squared is 36. 5 squared is 25. Adding all of it, we get 204. And then we get the product of these two. 10 times 2 is 20. 8 times 3 is 24. 2 times 9 is 18. 1 times 7 is 7. 5 times 6 is 30. 6 times 5 is 30. Adding all up, we get 129. Substituting into the formula, we are going to get a negative value, which is negative 0.94. Negative means an indirect relation. And because it's close to negative 1, then we have a strong negative correlation. So we have an indirect strong correlation, which means that if one of the variables increases, the other decreases. Again, indirect means if one variable If the value of one variable increases, then the value of the other variable decreases. Strong because it's near to 1. So the higher the stress, the anxiety level is, then the lower the test score will be. Okay, for our third example, we have the relationship between the math score and the physics score and the test scores. Okay, so this will now be, I will have 14 data. Okay, and then substituting into the table, we are going to get 0.8819. It's positive, therefore there is a direct correlation, which means that as one variable increases, the value of the other variable also increases. It's near to positive 1, so we have a strong direct correlation. Okay. So that will be for our correlation coefficient. So now we need to test the population, testing a population correlation coefficient. We need to test whether the correlation coefficient that we have computed is actually accurate or not. So after computation of the correlation coefficient from the sample, we would like to determine whether there is a sufficient evidence to conclude that the population correlation coefficient R is significant or valid. We'd like to know if it's significant or whether it's valid. So we perform a test and make a decision based on a set of level of significance, either 1% or 5%. So the level of significance that we're going to use is either 1% or 5%. So the hypothesis testing for R can only be one-tailed or two-tailed. We will be using the same procedure we had last meeting. So left-tailed, if the null hypothesis is greater than, if the correlation coefficient is greater than or equal to 0, the most significant negative correlation. If the alternative hypothesis will be if the correlation is less than 0, then there is a significant negative correlation. So we will now determine by the value of R that we were able to compute. So we will be using a t-test for the correlation coefficient. Unlike we had last meeting, it was a c-test. Now we will be using a t-test wherein we are going to use a t-distribution with n minus 2 as degrees of freedom. Okay, and we will be using the test statistic is R, and the standardized test statistic is this formula. The correlation all over the square root of 1 minus the square of the correlation coefficient all over n minus 2. R is the correlation coefficient. N is the number of data that we have collected. So let us now test the test scores of students in math in relation to physics. That is the last example we had. Okay, where did we get that? Going back, this is it. Okay, so this is our computed correlation coefficient, 0.8819. Would like to determine whether there is a relationship between the physics and the math test scores. But since this is positive, our conclusion was we have a strong direct correlation, which means that as the grade in math goes up, the grade in physics also goes up. There is a strong direct correlation. So we're going to use this correlation coefficient for our next example. Okay. So the scores of students in math and physics have a strong positive relationship, which means that if the score of a student is high in math, it can be expected that the score in physics test will also be high. So we will be using the same procedure we have for the hypothesis testing. So first is we now make our hypothesis. Now since our correlation coefficient is equal to 0.8817, then our null hypothesis is there is no significant correlationship between the math test and the physics test. And our alternative is there is a significant correlation between the math test and the physics test. Second, we now use our level of significance as 5% or 0.05. Because there is no relationship, then we will be using a two-tailed test. With our level of significance as 0.05 and n is equal to 14. 14 because we have 14 data. We use the table to find the critical values of degrees of freedom. So n minus 2 is equal to 14 minus 2 is 12. And these are the values. Positive and negative 2.179. From the t-distribution table, we're going to see that if the data is 14, then we're going to look at the level of significance as 0.05. And we got this. Where did we get 0.179? We got this from the table, t-distribution. And the sample correlation coefficient is 0.0019. And the test statistic is, we compute for the test statistics, we are going to solve it, we get 6.48. And again, 6.48 is greater than the critical value of positive 2179. Therefore, we reject the null hypothesis because 6.48 is greater than the tabular. Since it's greater, it would now fall in the rejection area. Therefore, we have to reject the null hypothesis. So at 5% significance, there is enough evidence to conclude that there is a significant linear relationship between the math and the physics score of the students. So we are actually saying that what we have computed is actually valid. So for our written output number 7. So the table below shows the time in hours spent by 6 students in playing Clash of Clans and the scores the students got in math tests. So we determine whether they are correlated or whether it is significant or not. So the time will now be represented as x. X is the time in hours. X is time. And the y is now the scores in math test. Y is the scores in math test. So if you played only 1 hour, you get a score of 30. If you played 2 hours, you get a score of 25. If you played for 3 hours, then the score is also 25. If you played for 4 hours, the score is 10. If you played for 5, the score is 15. If you played for 6 hours, the score is 5. So these are the data taken from 6 students. Okay, the first data, the first child played for 1 hour. The score he got for the math test is 30. The second child played for 2 hours. The score he got was 25. The third child played for 3 hours. He got a score 25. The fourth child played for 4 hours. He got 10 score in math. The fifth child played for 5 hours. He got 15 points in math. And the last child played for 6 hours and he got a point of 5. So here for number 1, all you need to do is give me the correlation coefficient. Okay, for number 2, a study was carried out to determine the relationship between the age and the time in minutes needed to run a 12-kilometer marathon event. The table below shows the data recorded. So, age is X, time is Y. You now test significance of the correlation coefficient at 0.05. At 0.05, with 2, 4, 6, 8 data. So first is, remember, you have to also get the table in the t-distribution. Under, we have 2, 4, 6, 8 under the column of 8 of 6 and minus 2. So under the column of 6 at 0.05 level of significance. And lastly, the speed of sound is said to be related to the distance or the altitude it travels. The following data shows results of some experiments relating these two variables. Now you are to test the hypothesis that the coefficient of correlation is greater than 0 against the alternative correlation coefficient is less than 0 at 0.01. Okay, so again, if there is any question, please feel free to send a message so I can answer you back. Okay, good luck.